Hi, my name is Elijah Ritchie, and I, along with Jake Malone and Noah Choate, will be presenting Big Data Project 1, which goes over different dimensionality reduction techniques and takes a deep dive into each of them. So first off, we're going to start with dimensionality reduction embeddings using various normalization techniques and checking out how these different normalization techniques and embeddings will work for the iris data. So the different embeddings we are going to do are PCA, sparse PCA, TSNE, UMAP, and LLE, which stands for local linear embeddings. And we're going to visualize all of these for the iris data, and we're going to use 5 different normalization techniques and on each, and also calculate the LCI for each of these as well. So there will be 25 total visuals produced and 25 total locality conservation indices calculated for each combination. So let's start off by looking at the PCA visuals. So right off the bat, we notice that min-max scalar and the max-ab scalar had the best clustering performances. All three classes are very distinct, and you can see that, and we can speculate that that is because min-max scalar and max-ab scalars will exaggerate the distances and between the points and allow PCA to pick up on these distances more easily. The standard scalar had a pretty decent performance. It conserved some locality, and while there is some um, cluster confusion between the what's it, Virginica and Versicolor, which is that's just a part of the iris data, and it just shows that this is properly representing the iris data. The robust scalar is similar to standard, except it distorts will add more distortion just because the iris data doesn't have so many outliers. And the power transformer is also similar to the standard scalar, and it just centers the data to be more Gaussian-like. So we noticed, I just explained all of these points on that previous slide, but just reinstating that max ab scalar worked the best, or the min max scalar, sorry, worked the best, and max abs was also good for clustering performance. And standard power transformer and um, robust all kind of had some confusion for the classes. Okay, and let's move on to sparse PCA. So sparse PCA is pretty similar to PCA, it's just geared towards data with more sparsity, more zeros. And while this doesn't particularly apply to the iris data, we can still test it on it. So we can see that the locality conservation is not quite as good as PCA across the board, but you can see similar patterns with how the data was clustered. Min-max and max abs um had the best clustering, but then it also seemed to have created some artificial separation, which may or may not be ideal depending on the task. Standard scalar and power transformer also behaved pretty similarly along with robust scalar, and they just have similar concepts from how they were carried out, so this makes sense. Um, So the TSNE was the best performer across the board for all of the dimensionality embeddings we performed in this part one of the project. Um, as you can see, the locality conservation ratios are very high across the board compared to the two PCA models we just went over. And you can also see that 4 out of 5 of these visuals will have distinct, or actually 3 out of 5 will have completely distinct clusters. Robust scalar just adds some distortion, as I said earlier, since there's not many outliers in the iris data, and the standard scalar has a pretty consistent performance between PCA and TSNE. Also, it's also important to look at how the power transformer result in similar embeddings to the standard scalar. This is just due to the iris data being already kind of centered, and the power transformer doesn't change it too much. The the min-max scalar had a better clustering performance than standard, but this does not mean it's necessarily better. It's better for separation, but it's not representing the um, data as well as standard. So UMAP, this was the second best performer in terms of embeddings. It had actually the best clustering. However, the locality conservation wasn't nearly as good as TSNE. There's like a little significant difference between most of these different normalization techniques. So yeah, UMAP, this is probably because UMAP kind of balances local versus global patterns, and TSNE kind of mainly focused on local patterns. So we can infer that the iris data probably has some very important local patterns that assist in separation of clusters. Um, as we can see, the robust scalar again causes distortion. The max av scalar works decently, but it kind of compresses the structure, kind of like the min-max scalar, except a little more extreme. And the power transformer also has a decent performance, but not quite as good as the others in this case. LLE actually yielded some pretty interesting results. The min-max scalar and the max-av scalar kind of crashed on this embedding model because it they the LLE is made for data that is not structured like as clusters, more as kind of a continuous manifold. So, um, yeah, the max abs and max scalars did not perform well, obviously. And then the standard scalar was the best performer, kind of had the most realistic data representation. The robust scalar again had a weird turnout, but it actually preserved most locality in this case, which I thought was very interesting. The power transformer also had a decent performance compared to the others, but still not very strong as the clusters don't seem to preserve much local patterns. And then this kind of goes over what I just said. So for best visualization performance overall, TSNE with the min-max scalar was the best. Um, this is likely because the min-max scalar exaggerates distances and TSNE is able to pick up on local patterns very clearly with these exaggerated distances. And we also found that UMAP was the second most effective embedding technique for the iris dataset. And the main conclusion is that the iris dataset contains important local patterns that really aid in the classification of all these data points. So yeah, some other important points to point out are that the robust scalar showed weak performances across the board. The standard scalar showed decent performances, and it's definitely the most consistent and usable for every model, but it wasn't like the most ideal for every model. And then Power Transformer performed well, but generally worked worse than Standard Scalar. And another thing is that the T-SNE, UMAP, and LLE models were all very sensitive to the N neighbors parameters, which indicates the importance of properly capturing the local structures in this data set. Okay.
All right, so here's the drug discovery part. Noah, I'm going to be reviewing this section. So our first order of business was just pre-process and then to pick a binary labeling system. And so for this, we decided to make the labels low sensitivity and high sensitivity, which was based on their overall response profile. This was done by calculating the average IC50 value for all 98 drugs, which you'll see in the visuals. Drugs labeled 1 or red indicates high sensitivities, and drugs labeled 0 or blue means low sensitivities. And this method gave us a balanced binary classification with around 50% of all drugs falling into each category. So here's our PCA visual. And as we can see with the labels, it makes a pretty good distinction of two clusters with blue and red. But with our PCA with the outliers, whenever we did it in the outlier plot, we can kind of see that all of the red or the high sensitivity drugs were on the outside of the main cluster. And so using the distance formula, we can see that while there was some of the red, there was mostly blue in the outlier category. And that's probably because this plot just used 2D structure and not three dimensionals or more. And so it doesn't really account for, all the space possible rather than just the 2D plane. In our T-SNE visualization, we can kind of see the same pattern of just two distinct clusters with almost a line down the middle. And while we do see some in the Stiesney labeling plot that are interconnected, most of it follows the pattern of a Great Divide. In our DB scan, we can see one huge cluster and then some purple dots, which indicates noise in the data set. And so that noise probably is just unusual drug response profiles, which do not necessarily fit well into the main cluster, which kind of suggests that these cells may have some unique biological characteristics. In our UMAP, it's almost the same exact story as our TSNE. We can see even smaller amounts of noise, which again probably means that these are probably similar to the ones in the TSNE that again share a unique drug response profile. Our LLE, this is kind of a different story here. Again, with our labeling, we can see almost a great divide with the blue and red. However, with our DB scan, we can see three distinct clusters different from the two. Indicates that LM or LLE algorithm believes there are three meaningful subgroups within the data. This is what's likely due to LLE's emphasis on preserving local structure, which can aid the discovery of subgroups within a data set. So our main takeaways was that the initial visualizations with our binary classification showed a clear separations between low and high sensitive cells, validating that our chosen binary labels did capture some meaningful differences. The DB scans, however, really showed one main cluster with just some additional noise of TSNE and UMAP, but the LLE DB scan showed three distinct clusters, which suggests some biological subtypes within the dataset, which makes sense because LLE is known to emphasize local structure. Overall, with our use PCA visual, we found rather linear relationships. In our TSNE and UMAP visuals, we kind of revealed the nonlinear structure and saw the more complex characteristics of the drug response patterns. Our LLE visual identified various subgroups within the dataset beyond our binary classification system and as we implemented in the start.
All right, so for part three of the problem, we're looking at the big patent data set. So to start off, we're going to look at the data set. It has 248,000 observations, 33 total columns, and that includes patent number, which is the unique identifier for each patent. And then the features 1 to 32 are unknown numeric attributes describing the levels of each patent, each observation, but we can infer what they mean in the world of patents and assume what they could be. And lastly, there's class ID, which is a binary target label, with 1 being the value for high value patents and 0 being the value for low value patents. So our first task is to look at a PCA analysis of the patent dataset and how to find special patents and what they are. So each observation is currently in a 32-dimensional space, which is hard to recognize outliers in. So we're going to use PCA to flatten the data set out and draw out special patterns by taking the top percentiles of outliers. So looking at our visualization, we can look at the three PCs that we used. Two PCs we started off with and got 23% explained variance, which wasn't high enough. So we moved to three PCs to allow for a space that we could still recognize outliers in, but explain up to 35% variance instead of 23. And you can see the outliers highlighted on the outside, and the darker highlight there is, the further away from the core they are. And the way we calculated this was through a distance method, calculating the distance from the outliers to the core of their centroid and going from there to rank them on distance from the center of the cluster. So looking at the analytics behind our PCA, we ranked them on distance from their center, and we can see the top 10 of them here. They're all class 1 patents. So we can see that the more unique a patent is, it's going to be linked to being a class 1 patent. And further from that, we can look at the contributing features for each PC so that as we find these unique and special patents, we can look at what's driving them further away from the centers. So for each PC that we saw in our visual, we can look at the top contributing features that are driving each direction of the graph. And from that, we can combine them to create a feature difference ranking between all of the points and the features so that we can find out not only what's driving the PCs, but more importantly, which features are most important in creating a patent that's special. So looking at this, we can see that number 25, 26, and 10 of the features are the most important drivers of these special patents. So, thinking about what that could be, we don't know for sure by name what they could be, but a likely possibility would be things like number of claims on the patent, or amount of funding for the patent, or maybe geographic area of invention, or some keyword novelty in the text of the patent that could be differentiating these patents from all of the others. So anything that could set one patent apart from the rest could likely be these things that are driving them away. The next step for this is calculating a t-SNE UMAP for the dataset and doing k-means clustering to calculate the accuracy and other clustering indices for the embedding data. So PCA was able to discover linear trends and draw conclusions of features and outliers through that, but there remains a lot of hidden structure to discover, subtle relationships that linear analysis can't capture. UMAP excels in mapping high-dimensional data in a 2D space while preserving both local and global relationships. Instead of treating every feature equally, UMAP will build a graph of similarity between patents and then unfold it, allowing us to see natural clusters that PCA would have flattened out. K-means, on top of that, will give us a quantitative confirmation of the visual landscape UMAP provides, looking at that through an accuracy score, silhouette score, ARI score, and Davies-Boolean score. Together, it'll help identify which regions correspond to the special high-value patents if we can find further nonlinear structure past what PCA revealed. And looking at the results from that calculation, you can see our accuracy score is 0.55, silhouette score is 0.43, adjusted rand index is 0.01, and Davies-Boolean is 0.9. So the UMAP embedding revealed the clear structural patterns in the patent data, showing that many patents naturally group based on feature similarity. The k-means clustering achieved moderate accuracy and a solid silhouette score, indicating reasonably well-defined clusters. However, the very low ARI suggests that these clusters don't perfectly align with the high versus low value patent labels. This means that while UMAP successfully uncovers meaningful relationships in the data, patent value likely depends on more complex or external factors not fully captured by the numerical features alone. To move into that next, we have fate and k-means to address the next part of the problem. Fate is the potential of heat diffusion for affinity-based transition embedding, similar to t-SNE and UMAP, but with a focus on gradual transitions rather than discrete clusters. With so many features, it is likely that the patents don't form sharp clusters all of the time, or there are patterns to be drawn from the gradual changes in between the clusters. Fate will preserve these relationships, where UMAP and t-SNE will cut them out. If successful, Fate strengthens the argument that the dataset contains meaningful structure beyond random variation. Alright, looking at the results, we can clearly see that Fate supports the existence of patterns beyond what was found in PCA and UMAP. We can see that patent value gradually increases with more complex feature combinations, rather than just in sharp groups. You can see this by looking at the differentiating between the orange and the blue dots, signifying class 1 and 2. As you move up and across the graph, you get more class 1 patents as things become more complex. And so this fate visualization complements UMAP in that it shows how the features are pushed to the groups where they are in UMAP. The next step was combining a 90% explained variance PCA analysis, t-SNE, and SVM. So previously we had used 3 PCs and described 30% variance. Moving up to the 90% explained variance, we now keep 22 components. Although much larger and complicated, it keeps more of the important data while only cutting out the noise. This will keep a solid amount of data for t-SNE to work on, but make it slightly more optimized, allowing for t-SNE to focus on the strongest signals. SVM will quantifiably check if the discovered patterns correspond to real class differences. Through the t-SNE done on the 90% PCA data, we can see clearer neighborhoods and clusters as t-SNE has less work to do and can focus on more important data, allowing for clearer analysis. Using SVM on the t-SNE data, revealed curved boundaries that linear analysis could not find. The high-value patents form locally tight, non-linear regions in the t-SNE embedding, validating the earlier clustering insight that patent value follows complex feature interactions. The nonlinear embeddings, UMAP, FATE, t-SNE, uncover clear structure in the patent dataset that PCA alone cannot. High-value patents differ not just in scale, but along multiple correlated dimensions that interact nonlinearly. Making these advanced visualization and clustering tools is essential for insight.
All right, that's everything.